Hey, how's it going? This is Team Dyn0m1t. My name is Arnold, and this is Houston. Our project goals for this project is going to be first, to use the encoder feedback to more accurately determine the position of the Roomba. 2 will be to integrate the new ZX gesture sensor to control the Roomba. And 3 will be to add a visual feedback to the remote so that it can be operated without line of sight. 2 of the major components for our project are the remote control system, which houses the embed, the OLED, and the gesture sensor, and the ground Roomba system, which has the BBB and the power supply.
Here's a slide of the remote control system. You can see the Zigbee, the OLEDs, there's 2 of them, the ZX sensor, and the embed, as well as a push button. There is also an accelerometer that is in this photo, but is unused for this version of the remote controller.
So here I'm going to describe the ZX gesture sensor features. It's a touchless sensor. It has 2 infrared LEDs and 1 infrared receiver. It has a C-axis recognition for about 10 inches and an X-axis recognition range of around 6 inches. It supports 4 gesture commands, left, right, up, and Z, which is going away from the sensor, and operating voltage of 3.3 to 5 volts. We had some minor issues. Some of the problems we encountered with the sensor was porting over some Arduino libraries, and also some small integration issues, which took away some of our time.
Also, the sensor did not work as well as advertised, and the gesture recognition on it was very flaky. So here's the Roomba ground system. There's a Roomba underneath that panel. You have a BBB BeagleBone Black, aka a BBB. You have a power supply USB, and you have a Zigbee. The BBB then controls the Roomba through the serial port that is attached to the USB hub on the back of shown at the top of the screen. There's also a Wi-Fi dongle attached to the USB hub for a debug console. The BBB is powered by the power supply, and the power supply goes through a separate USB hub in case we want to power other USB powered devices, such as other embed. Recording.
In this slide, we have the 2-wheel motor encoder positioning equations. We have the forward distance traveled as displayed here, and then we also have the radians turned. And also, for a complete derivation of how we got these equations, you could check this link here on this slide. For the Roomba dimensions, we have a wheel diameter of 72 millimeters. The wheel circumference is displayed here at 72 times pi millimeters. The wheelbase is 235 millimeters, and the encoder counts per revolution is 508.8.
To request the encoder data, we sent the ASCII values 148 to 43 and 44. The 148 is the stream opcode to make the Roomba stream data every 15 milliseconds. 2 is the number of sensors we are going to request. 43 and 44 are the identifiers of the left and right encoders. To parse the encoding data, you poll for the character 19 and then complete the parsing of the packet, which includes CRC checks and other pieces of information. We implemented the control loop using threads. We had 1 thread for updating the Roomba's velocity. We had a separate thread for calculating the position. We used the threading.condition object in Python to notify from one thread to the other thread when there was new data. The algorithm was based on reaching a goal as the robot. The tangential error is the error in the direction of desired travel. The perpendicular error is the error perpendicular to the desired travel direction. And the current heading is where the robot is currently facing. The The algorithmic logic is to assume that there's a maximum angular velocity error and make your angular velocity correction proportional to the perpendicular error. The advantages of this is it corrects for calibration errors between the wheel velocities, and it adds tolerance to the initial starting angle. So the overall control algorithm is to turn to the general direction of the target location, calculate the error tangential to the robot's heading. If it's within tolerance, don't move. Calculate the perpendicular error for the expected straight line heading and the target point. The target point is more than 10 inches away. Scale the calculation down to avoid overly sensitive reactions to tiny errors in angle. Calculate a corrective angular velocity. Apply other limiting factors such as not driving wheels in reverse while doing a forward trajectory. With these factors in place, we come up with a drive value for the right and left wheels.
So now we're going to go over to our demo video.
So here is the remote control. This is the operation. You hold it over the left side to turn left, and you hit the button to send the command. You hold it over your hand over the right side, and you hit the button to send the turn right command. You remove your hand and you click the button to send the forward command. As you can see, the robot's position is updated, including its direction. So you can navigate fully just from the OLED.
There'll be no line of sight required to navigate the robot.
On the left we see the robot with only dead reckoning. It will go off the rails rather quickly. In the middle we see the robot with dead reckoning updated by positioning assessments every 10 inches. On the right we see the encoder feedback loop operating every 150 milliseconds approximately. It works well.